Hi there, how's it going? Welcome to this video for the tutorial on stress transformation, failure criteria and FEA. I'm not going to do any finite element analysis demonstrations, but I will be making use of some of the results. And I did do a little video on how to use SOLIDWORKS to do FEA, so you can refer to that. Yeah, I'm not feeling all that well, so I missed the second class's tutorial this week. But anyway, here's the video for the tutorial. Let's get into it. All right, so in the tutorial, we didn't get through everything in the PowerPoint slide. So we'll just see how we go, how long it takes me to do a one-way delivery without all the discussion that we have in class. So, which is really what the tutorial classes are for, is really for engagement and discussion about things. So I'm not overly focused on getting through everything. Really, my main focus is on being able to discuss things that we need to discuss. Yeah, and I can do the one-way delivery of other stuff here. Anyway, so stress transformation, failure criteria, and FEA. So many of you, or you would have all come from different backgrounds. Some people would have done applied mechanics and design B, others haven't. So it's a bit difficult to do this topic, but yeah, I wanted to do it before we get into the machine design part of it, where we make use of some of these things. So some of it will be revision for some people, and some of it will be new to others. So anyway, so the way I'm going to do this tutorial is by making use of the problem that's in the design textbook that we have for this subject, and it's example 5.4. So you can have a look at that as I'm going through this tutorial as well. Oh, excuse me. Yeah, so this is the problem, and in the textbook it says design this bracket, which is made by welding this rectangular bar here to the circular rod, which is then attached to some rigid surface. Design the bar to carry a static load of 1,000 newtons. Right, so fairly simple problem, and one that covers a lot of what you would have done in applied mechanics and design A. If you did the subject with me, I would have asked you to design a torsion bar, and this problem is similar to that. Anyway, but before we do that, one thing that I did want to do is to ask you to have a look at the diagram and the problem that's presented, because there's a few problems with it. So firstly, have a look at the diagram and just see what you can see problems with it, where there might be inconsistencies, where things don't line up where they should, and so on. All right, so stop the video and do that. Okay, so hopefully you've done that and found some problems with it. You know, part of this is just to point out to you how important it is to convey information correctly. In past subjects, you know, I may have, well, I would have focused on making sure that you do your diagrams well for free body diagrams and so on, making sure your witness lines go to where they're meant to go, making sure your axes going in the right directions, because it's important, right? It's not a bit of art. It's a way of communicating and conveying information about a mechanical component, machine component, structural component, whatever it is, right? And someone reading it has to be able to interpret without any ambiguity what it is that you're trying to tell them. All right, so this is what I found with the problems with the diagram. We've got two z-axes here. What's going on there? Well, there's inconsistency there. Also, this z-axis down the bottom here, if we look at the x and y axes, it doesn't follow the right-hand rule, right? So if we have our fingers and we put our fingers in the direction of x and then curl them in the direction of y, our thumb should point in the direction of the positive z-axis, okay? So should be pointing upwards, the same as we've got over here. This axis here. I'm not sure what that's supposed to show. I assume it's meant to be a horizontal axis that's parallel to the top and bottom edges of this backing plate here, parallel to the y-axis of this rectangular bar, but it hasn't been drawn like that. So we're left thinking, what's going on here? Why is it like that? And if we look at what's happening here, the locations of the axes and the witness lines for the dimensions aren't quite correct. Right? So this y-axis, I'm assuming, should be at the center or along the centroidal axis of this rectangular cross section, right? But it's not. And because it isn't, then up here is inconsistent or ambiguous, not quite sure what's happening here. Right? So this hasn't been drawn particularly well either. So make sure you do your drawings well and leave no room for ambiguity or inconsistency. Okay, so as a design process, we need to make a choice about material. Right? So that would be one of the choices that we have to make in a design task. In the textbook, they've said, okay, we're just going to choose this particular grade of steel. And then from that, we need to make use of the material properties or mechanical properties of that material. So you should be used to looking up these material properties. So have a go at finding the appendix in MOT or anywhere else you like. I like to use the online materials catalog MatWeb. So you can look it up there and find the relevant material properties. So ultimate tensile strength and the yield strength or yield stress. So go and do that and then come back. All right, so hopefully you've done that and found something similar to this. So we're going to use these strengths, or the example in the textbook uses these strengths and the design factor of 2 to determine what the cross sections of these parts of the bracket should be. And I'm just going to use SI units and dimensions that are similar to what they came up with in the textbook example. So the diameter of the rod is 25 millimeters, the height of the bar is 30 millimeters, and the thickness or width of the bar is 10 millimeters. And the other dimensions here are given. Length of the cylinder or the rod is 200, length of the bar is 300 millimeters. Okay, so starting with the rectangular bar, what is or are the loading modes on this beam? Okay, so have a go at thinking about what they might be. Right, so hopefully you've done that and you've come back and I've listed them all here. So these correspond to, back in Applied Mechanics and Design A or Mechanics of Solids, you would have had the Hibbler textbook probably for Mechanics of Materials. And it would have been broken up into chapters like this. So we had axial loading, bending, probably wasn't the next one. Bending is usually a bit later in the textbook, usually around chapter 5 or 6 or 7, somewhere like that. Torsion, direct shear, and transverse shear. Okay, so difference between direct shear and transverse shear. Direct shear is kind of like, you know, if you did engineering studies at school, people will talk about the scissors shearing, or, you know, if you got a piece of material like this and push down on one hand and up on the other, you've got a shear plane here. Okay. Back in Applied Mechanics and Design A, we looked at mechanisms and pins, or frames and machines, and we looked at the pin between two members, and where the pin went through between the two connecting members, there was a shear plane there. Okay, so we had two forces either side in opposite direction, creating a shear on a shear plane. Okay, so that's usually what we refer to as direct shear. Transverse shear comes about from bending, right? So some books, and including the Mott textbook, refers to this shear as shear due to bending, okay, which is really what it is. Okay? But the Hibbler textbook and I think maybe the Beer and Johnson textbook, another common one for mechanics and materials, talk about transverse shear. Right? And then torsion is your twisting loading. Right? All right, so what have we got in this beam here? Right, there's no axial loading bending. Right? So we've got a lateral load out here, supported at the other end. So we've got kind of a cantilever bending going on there. No torsion, no direct shear, but we do have bending. So we may have, and we will have transverse shear developed in the beam. So we're going to do a bit of revision and look at what you studied back in Mechanics of Solids, Fundamentals of Mechanical Engineering or Applied Mechanics and Design A. All right, so for bending, what's the equation for bending? Hopefully you've come up with that. Most people would say stress is equal to my upon I for the stress due to bending. And we need to determine what these things are in this equation. Okay, so firstly, the M is an internal bending moment. So whenever you look up the formula for stress and there's an M for bending moment, that M is the internal bending moment. Okay, so there's no external moment applied here, as we can see, like a curly arrow to represent a concentrated moment being applied. We've only got the single force out here, right? So this moment here in this formula refers to the internal bending moment, right? And really, we should then, when we want to determine the stress, take a cut where we want to find the stress. So the other thing about this equation is that it's for a single point somewhere in the component that we're analyzing. So we have to decide where do we want to know the stress, and at that point we need to know the internal bending moment acting on the cross section. So we'll get to Y and I in a second. Yeah, so here we've taken a cut somewhere, drawn a free body diagram, and we've got our internal bending moment and internal shear force. And we can draw the shear force and bending moment diagram. Okay. Where will the maximum stress be? So let's have a look at the equation. So firstly, the moment, we look for where the maximum moment will be. So if we wrote our moment equation here, the direction along here is Y, we would have the moment equation, M is equal to F times Y. So the further we get away from where the load is to our cut, the larger the moment is. Right? So our maximum bending moment is going to be at the supported end here. All right. On this cross section, where is the maximum stress going to be? So you probably know that if we have something like this, right, and we try and bend it, so if we're pushing downwards on the end here, on the top will be, what's it going to be on the top? Tension, that's right. On the bottom, in compression. Right, so it goes from positive to negative. So somewhere in between must be zero. Right, so the maximum stress is at the outer fiber. Okay, so this Y here in this equation is telling us the distance from the neutral axis to the outer fiber. And then I stays the same throughout the length. So I is the second moment of area or the moment of inertia. So our maximum stress will be at the supported end, where the internal bending moment is maximum and where Y is maximum in this equation, right, which is the outer fiber. Okay, so is it at element A? So that's what the textbook is tending to indicate, right? So the maximum is at element A. So if we do our calculate our internal bending moment at the point where A is, the cross section where A is, the bending moment here is equal to force times this length B. Anywhere along here, between where the load is applied and where it's supported, it will be F times what we called here Y. So this is getting a bit confusing, right? So there's a Y here and there's a Y here. And we'll get to that, dealing with that in a second. Okay, so what is Y in this equation? Right, we've said that in this equation, it's the distance from the centroid in the cross section of the neutral axis, or the neutral axis, to the outer fiber. Right? So here we shouldn't really have Y in this equation. Really, it's Z according to this coordinate system that we've used. Right? So for the axes that we've shown, for the bending equation, we actually need Z here, not Y. Right? So an alternate form of this equation is mz over I. Or it could be mx over I, right? Depending on the coordinate system and the axes that you're making use of. Right, so if you're just taking this formula, oh yeah, it's my upon I, y is 300, and you put that in, right, you're going to get the wrong answer. So it's important that you're able to understand these equations and apply them correctly. Okay, so Z is just h over 2, so the distance from the neutral axis to the outer fiber. Calculate the cross-sectional moment of inertia. So what's the moment of inertia for a rectangular cross-section? VH cubed upon 12. Hopefully you remember that. So have a go at calculating this value, or the value for the moment of inertia, or the second moment of area. All right, stop the video and do that. Okay, hopefully you've done that, and we get, right, the first thing to do is to make sure we're calculating the moment of inertia about the correct axis. So here, about the x-axis. And right, I said BH cubed upon 12 before. I've used here TH cubed upon 12, just to clarify that we're using this cross section. If you look down in the bottom left-hand corner of the screen, where my mouse is, right, this rectangular cross-sectional face here. In the tutorial, a few people get this wrong and get something like 6.75 times 10 to the something, depending on whether you're using millimeters or meters. And that's because they've used B equal to 0.3 in here instead of using T or B equal to 10 millimeters. Right? So not an uncommon mistake to make. So if you've made that mistake in calculating this here, don't worry, learn from it, and then just make sure that you understand properly what you're calculating. All right, so let's move on. So I've just converted that to meters. So some people work in millimeters, some people work in meters, and we'll look at how that affects things in a second. All right, so working in newtons and meters to now calculate the stress. So we've got all our terms. We've got the moment, we've got Y or Z, as it is for the coordinate system that we have here. And we have our moment of inertia. And excuse me, I'm just going to, oops, I'm going all blurry. Better. All right, working in newtons and meters, we get our answer for stress in pascals. Okay, so we get 200 by 10 to the 6 pascals. And we can convert that to megapascals because 10 to the 6 is the prefix mega. Right? All right, we can also work in newtons and millimeters. So have a go at doing that. All right, hopefully you've done that, and you can see if we work in newtons and millimeters. So newtons and millimeters for our moment, millimeters for our distance from the neutral axis to the outer fiber divided by millimeters to the fourth. All right, so you can see here, right, millimeters times millimeters becomes millimeters squared over millimeters to the fourth. So we get newtons per millimeter squared. And our answer comes out in megapascals. So your calculator doesn't have megapascals or pascals after it. It just has the number. Right? You have to interpret or firstly make sure you're putting in consistent units into the calculator, and then interpreting what the calculator is telling you, and writing the correct units next to that number in your analysis. All right, can you draw the stress element? So an important part of doing stress analysis and then doing design for strength is to understand what the stresses are doing. So typically what we would do is to represent the point where we're finding the stress as a square. Now, in the textbook, they've got this little rectangle on top of the beam, but the stress element that we've drawn here is actually from looking from the side. Right? So have a go at putting on the axes and then putting on the stress. So stop the video and do that. All right, so firstly, put on the axes. Oh, in fact, I've got the stresses first this time. All right, so let's have a think about what's happening again. We've got our beam. Hopefully you can see me clear enough just in my little video of me in the corner. So on the top, we had in tension. Okay, so if the top is in tension, it's being stretched along the length of the beam. Right? And that direction, according to our axes that we've got drawn on here, is in the y direction, right? So we can put on our coordinate system like this. Okay, so it's being stretched on the top in the y direction. So this is what we have here for our stress element. And then when we write the formula, the symbol for stress, sigma, we put a lowercase y to indicate the direction of that stress. Okay. Right. And now completing the formula for stress and using all of the subscripts as appropriate for the coordinate system that we have. So we have stress in the y direction is equal to the moment about the x-axis times the distance from the neutral axis, or in this case the centroid, to the outer fiber in the z direction. So z divided by the moment of inertia about the axis that we're bending about. So moment of inertia about the x-axis. All right, I'm going to stop the video here at the end of this page, and we'll come back to continue on in the next part of the video. See you in the next one. Bye.